free expansion and isothermal process. So what is free expansion? Free expansion is that expansion when the outside pressure is zero. Means we are doing expansion in vacuum. So expansion of gas in vacuum, that is external pressure is zero, is known as free expansion. Means there is no blocking agency, there is no blocking agent outside. So that's why we say it is free to move, free expansion. No work is done during free expansion. This is slightly tricky to understand. You might think that because piston is moving, there is some work being done, but in physics, it is zero. The reason is the work is given by minus P external delta V. So although change in volume is taking place, but P external is zero because it is vacuum, so it will be zero. So work done in free expansion will always be zero. Then isothermal process. Isothermal, iso means same, thermal means related to temperature. So same temperature. Temperature does not change during the process. That is known as isothermal process. So Joule experimentally determined that for isothermal process, the change in internal energy is zero. So remember, isothermal process, delta U is zero. Hence for isothermal process, first law of thermodynamics gives us Q plus W will be 0. If Q plus W is 0, Q will be equal to minus W. So whatever formula you have for work, you can apply for heat in case of isothermal process only. Remember, these formulas will be applicable only for isothermal processes. Whatever is written here, few important formula I am talking about. For isothermal irreversible change, Q will be equal to minus W, and W you knew. W is minus Px delta V. So minus and minus will give you plus. So that's why Q will be P external into delta V, only applicable in case of isothermal process. Okay. Then isothermal reversible process. In this case, there will be integration. If you solve the integration, it will be 2.303 log something. Okay. So I will be using Q equals to minus W. It is isothermal process. Delta U will be 0. So that's why Q will be equals to 2.303 nRT log Vf by Vi. Why? Because in this case, W is minus 2.303 nRT log V final divided by Vi. This minus and this minus will be plus. So that's why positive sign. Sometimes I have seen students making mistakes using negative sign here. Okay, remember, negative sign is only in the formula of work. Okay, not in any other formula we will be using in this chapter. Okay, apart from one I will be using for Gibbs energy towards last of this chapter, there will be negative sign. But here whatever we are talking about, internal energy, external energy, heat enthalpy, okay, work done, energy, whatever, only the work formula has a negative sign. Although the answer can be negative or positive, right? I'm not talking about answer. Answer can be negative if the work is done by the system. Answer can be negative if heat is evolved from the system. Okay. I'm talking about formula only. For adiabatic change, Q is 0. Okay. So for adiabatic change, we know that heat transfer will be 0. And if it is heat transfer 0, delta U will give you W adiabatic. So these formulas I will be using, you need to remember. The question: 2 liters of an ideal gas, initial volume 2 liters, at pressure of 10 atm, so pressure is 10 atm, expands isothermally. If it is isothermal process, delta U is 0. At 25 degrees Celsius means temperature is 298 Kelvin. In a vacuum, okay, so it was actually P initial, internal. Vacuum means P external is 0 here. Till the total volume is 10 liters means V final is 10 liters. Question is how much heat is absorbed and how much work is done in the expansion. So first we can calculate the work done. work done, because it is isothermal, obviously I can calculate the heat later on by minus W by using this formula. For isothermal process, delta U is 0, that is Q equals to minus W. But work can be obtained by minus P external delta V. And remember, it is vacuum outside, P external is 0. It means it will be minus 0 multiplied by delta V. Delta V will be final pressure, final volume minus initial volume. So it will be 0 into 8, that is 0. No work done. If no work done, obviously Q equals to minus W, that will also be 0. Isothermal process. So no work will be done, no heat will be done. So we have Q equals to minus W, W is minus Px delta V, which will be 0. So no work done, no heat absorbed. Next part of the same question. Now consider the same expansion, but this time against a constant external pressure of 1 atm. So we will apply the same formula. Q equals to minus W, because delta U is 0, it is isothermal process, Q will be equal to minus W. And here we will apply the same formula, minus P external delta V, but now P external is not 0, it is 1 atm. So we will substitute these values. P external is 1 atm and V final minus V initial will be 8. So answer in this case will be 8 liter atm. So if we say W will obviously be here in this case minus 8, okay, because W will be minus P external V final minus V initial. So it will be minus 1, 10 minus 2, that is minus 8 atm liter or liter atm. And it is negative. It means it is done by the system. Okay. This is plus. It means absorbed by the system. This much heat absorbed by the system. Positive on the system, to the system. Okay. Negative done by the system, from the system. Next part of the same question. Consider the same expansion, but we have now 1 mole. So N is given. Ideal gas conducted reversibly. So if it is reversible, you know the formula is integration formula, or 2.303 log V final by V initial. Obviously nRT will be there. So we will use that formula. It is isothermal. Q will be equal to minus W, and W here, if you remember, for isothermal process, reversible process, it was minus 2.303 nRT log V final divided by V initial. So minus and minus will get neutralized. So you will have 2.303 nRT log V final by V initial. Substitute all the values. We have 1 mole here. Substitute N equals to 1. R we have taken 0.0821. It means our answer will be in terms of atm and liter. So this value of gas constant, the unit is atm liter per Kelvin per mole. So it means this Q we will get in liter atm or atm liter if we use this value. If we use 0.0831, it will be liter bar in that case. Okay. If we use 8.314, then it will be joules. So depending on what unit you want as result, you need to take the value of R accordingly. Then we solve this one. Log 5 value is given. So substituting that, we solve, we get the value of heat as plus 393.66 liter atm. And because it is positive, it means this much heat will be absorbed and the same amount of work will be done by the system. W will obviously be negative because Q equals to minus W. Then change in enthalpy, that is delta H. H is enthalpy and change in enthalpy is delta H. We know that at constant volume, Q is equal to change in internal energy. Because work will be 0. Work is given by minus P external delta V. If it is constant volume, then delta V is 0. It means W will be 0. If W is 0, then delta U equals to Q plus W. This W is 0, delta U will be equal to Q only. But here we write V just to indicate that it will be equal to Q only if we have volume as constant. So writing QV indicates that it is at constant volume. Otherwise, delta U will be equal to Q plus W. But most of the chemical reactions are carried out in flasks or test tubes under constant atmospheric pressure. So we do the reactions in test tubes which are open. So it is actually the atmospheric pressure which should be constant, not the volume. So for that, the concept of change in enthalpy comes into picture. So delta U is equal to Q plus W at constant pressure. Delta U will be equal to QP, that is whatever is the heat transferred at constant pressure, minus P delta V. This pressure is there and change in volume. There will be change in volume now. Volume is not constant, okay, and pressure is constant. So from here, I will get U2 minus U1. Delta U is actually U2 minus U1. It is a state variable, equals to QP minus P delta V, and delta V is also V2 minus V1 state function. And we can now write it like QP equals to U2 minus U1, QP obviously here, U2 minus U1, and this one goes on the other side, plus P V2 minus V1. So I think that much math you know. Now if I rearrange this one, that I have U2 with PV2, so U2 plus PV2, and I have U1 with PV1, U1 plus PV1. So this term U2 plus PV2 or U1 plus PV1, that is U plus PV, this is known as enthalpy of that particular state. So state 1, state 2, this is known as enthalpy. U plus PV is defined as thermodynamic function enthalpy denoted by H. Hence QP is equal to H2 minus H1. This is enthalpy final. This is enthalpy initial. So H2 minus H1 will give you QP. So QP is actually delta H. H2 minus H1 is change in enthalpy. It is QP. So if you compare it, we said delta U is equal to QV. Okay, means if we keep the volume constant, whatever change in heat is there, whether heat transfer to the system or from the system, whatever change it's, that will be equal to change in internal energy. But if we keep pressure constant, then whatever is the change in heat absorbed or heat released, that will be equal to change in enthalpy. So two important concepts you need to remember. It will help you to solve numericals. Delta U is heat transfer when volume is constant. Delta H is heat transferred when pressure is constant. So although Q is a path dependent function, now you might challenge that here we are saying Q is equal to delta U, here we are saying Q is equal to delta H. Delta H and delta U both are path functions. It is H2 minus H1, means it depends only the difference between final and initial state. Delta U is U2 minus U1. It again depends on only final and minus initial difference, nothing else. So why we can say that here delta U, which is a state function, is equal to Q, which is path function? The reason is we are specifically saying volume is constant. If volume is constant, only then it will act as a state function. So heat will act as a state function at constant volume. Similarly, heat will act as a state function at constant pressure, and that will be equal to change in enthalpy. Okay. So delta H is independent of path, hence QP is also independent of path. QP is also a state function. Similarly, QV is also a state function. So delta H, delta U, QV, QP all are state functions, but Q is not a state function. If we say just heat, it is not a state function. Delta H is negative for exothermic reaction and positive for endothermic reaction, and it is very simple concept we have already talked about. If it is a system, whatever is into the system, whether it is work, whether it is heat, it is positive. Okay, whatever is outgoing from the system, whether it is work, whether it is heat, it will be negative. So exothermic reaction means heat is evolved. So this is exothermic reaction. Heat is evolved. It means delta H, which is QP, will be negative. But if it is delta H getting into the system, absorbed by the system, it will be endothermic reaction. It means for endothermic reaction, delta H, which is QP, will be positive. So endothermic reaction, delta H positive. Exothermic reaction, delta H negative. Then relationship between these two entities we talked about, delta H and delta U. Very important formula you will be using very frequently. We know that delta H is equal to Q plus W. For finite changes at constant pressure, we can write delta U equals to QP plus W. So if we are talking about constant pressure, which is normally the case, we do normally the reactions at constant pressure, then this heat transferred will be QP. And some work can be done because delta V is not zero now. Volume can change. Okay, so the reaction mixture can expand, can contract. So there can be change in volume. So W will also be there in that case. We can write W as minus P delta V. It means delta U can be written as, remember at constant pressure, it can be written as QP, that is delta H minus P delta V. Why delta U comes into picture? Delta U comes into picture because some work is also being done apart from heat transfer. So if we are doing any experiment, any reaction at constant pressure, it will ensure that heat transferred is QP. It cannot be QV. But at the same time, delta U appears because some work is also being done. So sum of these two will give you change in internal energy. QP we can write as delta H. So it means delta U is equal to delta H minus P delta V. It means delta H is equal to delta U plus P delta V. This is initial form which in few cases we will be using. Okay, it is not much used, maybe 20% times or maybe 10% times we will be using this one. But if we modify this one, that is the form we will be using very frequently of the same formula. So for two gases A and B, and it is applicable for initial and final state also. Although I have written here two gases, it will be applicable for the reaction also. So for example, if I have a reaction CH4 combustion of methane plus 2O2 will give you CO2 plus 2H2O. So in this case, this is gas, this is gas, this is gas, this is liquid. Okay, so initially I have methane and oxygen, different gases, and finally I have carbon dioxide, different gas. Okay, so it is initial and final case also, but in general I have written for two gases A and B, PV is equal to nRT. So because PV is equal to nRT, this is ideal gas equation. For gas A it will be PVA equals to NART. For gas B it will be PVB equals to NBRT, or maybe in initial state and in final state. These will be the two equations. So if we subtract the first one from second one, so if we do equation 2 minus equation 1, we will get PVB minus PVA equals to NBRT minus NART. If we take RT common, it will be NB minus NA. It means it is change in the number of moles. This is change in the number of moles, delta N. So we can write it as P delta V, because VB minus VA will be delta V. P delta V equals to, this one has been written as delta NG and RT. What is delta NG? Delta NG is actually the number of moles of products minus number of moles of reactants. This is the change in the number of moles. So if I take the example, same example I talked about earlier, combustion of methane. Remember, this is only true for gaseous moles. Okay, so as you see here, this is liquid. So if I have to calculate delta Ng, I will calculate only the gaseous moles. Okay, so number of moles in product side, 1 mole here of carbon dioxide, I will not consider number of moles of H2O. Although it is 2H2O, I will not write it because I will consider only the gaseous moles. Okay, so gaseous. So it is 1 delta Ng. In this case, G indicates gaseous only. Okay, so that's why Ng written here will be equal to number of moles of products will be only 1 minus number of moles of reactants which are in gaseous form, 1 here and 2 here, total 3. So it means delta Ng in this case will be minus 2. That's how you will calculate the value of delta Ng in numericals. This is very important, delta Ng RT. Now we can replace P delta V in previous equation, what we talked about here. In this case, P delta V can be replaced by delta Ng RT. So when we replace this, we get delta H equals to delta U plus delta Ng RT. Very important relationship you will be using throughout thermodynamics. And how do you remember that? It is of the form of HURT, H-U-R-T. So just remember, I usually call it HURT formula so that you don't get confused whether delta U is here, delta H is here. This is common mistake students do. Okay, sometimes students write delta U equals to delta H plus delta Ng RT, which is wrong. So remember, everything is positive. First of all, it is plus sign, it is not minus sign, and it is HURT formula. H for delta H, U for delta U, and then RT means delta Ng RT. Solids and liquids do not suffer any significant volume change, means delta V has to be 0 there. So if I go back to this formula, this one, okay, in this case, if I am talking about solid or liquid, the change in volume will be almost 0. So in that case, delta H will be approximately equal to delta U. There is negligible difference in volume. Remember, only in case when all the reactant and products are either solid or liquid, there are no gaseous form. Okay, so if we don't have any gaseous reactant or product, in that case only delta H will be equal to delta U. So in that case, delta H will be equal to delta U when no gaseous reagents or products. When no gaseous reactants or products are there. Now the question, if water vapor is assumed to be a perfect gas, means ideal gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. What is this molar enthalpy change? You know, enthalpy change is delta H. Molar enthalpy change is per mole. Okay, so if it is given as 41 kilojoule, and you see it is written as per mole here, okay, because if you have for 2 moles, it will be double. So that's why you have to quantify it for particular amount, 41 kilojoules per mole. It is given. Okay, so delta H for water vapor is given 41 kilojoules per mole, and pressure is given 1 bar. Pressure is 1 bar, and temperature is given 100 degrees Celsius, that is 373 Kelvin. All the calculations will be in kelvins for temperature. Okay, the question is calculate the internal energy change, means delta U, when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Means what's happening? 1 mole of water, this is liquid form, is vaporized, means now it is gaseous form. That is the first part of it. 1 mole of water is vaporized. So pressure is given, temperature is given, delta H is given, delta U is to be obtained. You will apply the HURT formula. Okay, you will not write in exam HURT formula. I am writing just to make you understand so that you can recall. Okay, you will say using the formula delta H equals to delta U plus delta NGRT. So delta U from here we have to calculate will be delta H minus delta NGRT. Delta H is given 41. Now very important point where students make mistake. It is given in kilojoules, and the value of R when you use 8.314, it is joules per mole per Kelvin. So value of R is 8.314 joules per mole per Kelvin, and you can't use two different units. So either you use delta H as 41 kilojoules and then convert this R also to kilojoules, or you convert this delta H to joules. Okay, so I'm using it as kilojoules, and I will convert I will convert into kilojoules. 8.314 into 10 to the power minus 3. Okay, if I convert it to kilo, I will have to divide it by 1000, that is multiplication by 10 to the power minus 3 kilojoules per mole per Kelvin. And what is delta Ng? It is important to understand what will be the value of delta Ng. This is the reaction. In this case, delta Ng is gaseous moles of product minus gaseous moles of reactant. Now here gaseous moles of product 1, because here it is in gaseous form. Here you don't have any gaseous reactants, means 0 moles. So it will be 1 minus 0. Okay, water is vaporized, final 1 mole gaseous, initial 0 moles gaseous. R 8.314 into 10 to the power minus 3 kilojoules per mole per Kelvin, and temperature 373. So when you solve it, you get the value 3.096. This value, when you simplify, 3.096. This one is because delta Ng is 1 minus 0, that is 1. So when you solve it, you will get 37.904 kilojoules per mole change in internal energy. That is the answer of first part. Now the second part. Second part is 1 mole of water is converted into ice. Now there is no gas. The reaction in second case will be you are converting the water to ice, means liquid to solid. And in this case, we will apply this formula. We can apply the other formula also. We can apply this formula also. Okay, I will show you that you can apply any formula in this case. So if we use this formula, is there any change in volume? No, we talked about that there is hardly any change in volume if there is no gaseous reactant or product. So liquid to solid will not result in any significant change in volume. Means this delta V will be 0. And if delta V is 0, delta H will actually be equal to delta U, or delta U will actually be equal to delta H. So in this case, it means you can write delta U will be equal to delta H, that is 41 kilojoules per mole. You can apply the formula delta H equals to delta U plus delta NGRT. In this case, delta Ng will be 0. Why? Because the final product, gaseous product 0, initial gaseous product 0. We have only liquid and solid, so gaseous moles 0. So delta Ng will be actually 0 minus 0, that is 0. So delta H will be equal to delta U, or delta U will be equal to delta H. Again, okay, so delta Ng is 0. So delta U will again be 41 kilojoules per mole. Now extensive and intensive property, these are just definition and very simple questions are asked. So if you remember the extensive, and I will tell you the way also how you can remember which one is intensive property, which one is extensive property. So first try to understand what it is. So suppose you have this container and it has a gas, the volume is V, temperature is T. Now if you place a partition, okay, you divide it into two equal halves. You see that volume is changing. Volume, new volume is half, but temperature is same. Temperature will not change. This gives us an idea about that all the properties are not similar. Okay, they are different. They are different in the sense that if we change the size, okay, if we change the size, their behavior or their value changes. So in this case, the one which changes, means volume, is known as extensive property. So the parameters, okay, which change with size or amount are known as extensive parameters, and they represent extensive property. Okay, so extensive property shown by extensive parameter. The one which remains same, intensive. Okay, so extensive property, property whose value depends on quantity or size, that is amount or size of matter present in the system. Extensive. So for example, mass. So if you divide one piece into two, the mass will change, volume will change, their internal energy will also change, because it is now half the mass, there will be half the energy. Enthalpy will change. So if you have this much amount and it has been heated up to some temperature and it has q amount of heat, if you divide it into two, this one will have q by 2 and q by 2 heat. Okay, enthalpy will change. Heat capacity, this is something I will be talking about later on. What is heat capacity? That will also change. Heat capacity is something that how much, how easily it can be heated. Okay, that is heat capacity, or how difficult it is to heat a particular matter. All these are extensive property. Why? Because if you change the size, the property will change. Intensive property, opposite. So if they do not change with size, these are intensive properties. So for example, you have seen temperature did not change, some same density will not change. So if I show you the same example here, whatever is the density of air here, the same density of air will be here. So suppose you have two rooms, okay, you have one room and you divide it into two parts, it will not change the air density in that room. Okay, so in your house, if you have 4 rooms, 5 rooms, every room will have same density. It will not depend on how big it is or how small it is. Okay. So density will remain same. Similarly, temperature will remain same. Also, pressure will not change. Okay, pressure will be 1 atm everywhere. It will remain 1 atm. So pressure also is intensive property. Temperature, density, pressure, these are intensive properties. Now, how do you remember, right? So it is easy to remember that pressure will not change around you, whether you are in very small room, whether you are in big room, or whether you are outside of your house. Pressure is same. Okay, you are experiencing 1 atmospheric pressure only. So it means pressure does not change. So it is intensive property. How you can remember it is intensive property? You will remember the keyword pin. Pin. Okay. You can remember this keyword. As I said, you need to remember the word Hert to remember the formula delta H equals to delta U plus delta NGRT. Similarly, remember this keyword pin. It means pressure is intensive property. And you know that pressure does not change. Okay, it is very well known fact that pressure in your room, in your house, outside, everywhere it is same. It means if any parameter is constant, it is intensive property. Opposite is for extensive property. Now the question, for the process to occur under adiabatic conditions, the correct condition is, in adiabatic system, we have talked about no heat can be transferred, only work can be done, heat cannot be transferred, and only the one which shows heat cannot be transferred, Q is 0, is the third one. That is the correct answer. Okay. Work can be done. Okay, because work can be done, obviously pressure can be applied, because W is equal to minus P external delta V. So you cannot say delta P is 0. Okay. Similarly, temperature can be changed when you do work. So for example, if you run a fan, it can increase the temperature. Okay, it will agitate the air, it can increase the temperature. So temperature may not be 0. So only the third option is correct, adiabatic condition, Q is 0. And whatever is the work done, if you remember, delta U is equal to WAD. Whatever is the work done, that is change in internal energy for adiabatic system. Now this is something which you should remember. These are the standard conditions. So whenever we say standard pressure, standard temperature, we actually mean by some conditions. So these are standard conditions. These will help you to answer the questions, few questions, and to understand the questions also. The standard state is the state of a material at a defined set of conditions. Means it is pure gas exactly at 1 atm pressure, sometimes 1 bar also. Okay, so in your chapter you will see that 1 bar will be termed as a standard condition. So if I say a standard pressure means 1 bar. If I say this particular gas is at a standard condition means at 1 bar pressure. Okay, it will be mentioned as STP also. If it is mentioned as STP, then it is a standard temperature and pressure. In that case pressure will be 1 atm. But standard condition, if it is just written a standard condition, it can be 1 bar, it can be 1 atm depending on the condition. It is pure solid or liquid, pure gas, pure solid or liquid, and in its most stable form at exactly 1 atm pressure and temperature of interest, usually room temperature 25 degrees Celsius. If it is mentioned as room temperature, that is the standard condition. Okay, if it is mentioned as STP, in that case it is a standard temperature and pressure, their temperature is 0 degrees Celsius. Okay, but if we are saying normal is 25 degrees Celsius. So sometimes it will give you a hint whether it is talking about room temperature or whether it is talking about STP. So mostly if it is talking about 0 degrees Celsius, in that case it will be clearly written as STP. Substance in a solution with concentration 1 m. So if we have a substance with molarity 1, we will say standard molarity. So 1 molar solution is standard. 1 atmospheric pressure is standard. If we are saying STP, the standard is 0 degrees Celsius. If we are saying normal temperature and pressure, it is 25 degrees Celsius, room temperature. Okay. Standard enthalpy change delta H naught. So another point you need to remember, whenever you see naught at the top, it means we are talking about standard. This is a standard parameter. Okay. So this is enthalpy change when all reactants and products are in their standard states. Then it will be delta H naught. And many a times I will be referring to delta H naught, not delta H. Okay. The standard enthalpy of formation, it is actually the standard enthalpy, but for a reaction when something is being formed of 1 mole. Okay, so if 1 mole of something is being formed and whatever change in heat will take place at constant pressure, you remember delta H is change in heat at constant pressure. So whatever heat change will take place at constant pressure for formation of 1 mole of a pure substance, that will be termed as enthalpy of formation, standard enthalpy of formation. Okay. So all the elements must be in their standard state. Delta H formation standard for a pure element in standard state is 0. This is very important. There's a question also on this one, that the standard state enthalpy is what? So standard state enthalpy for all the elements, pure elements, will always be 0. The reason is very simple, because if we are talking about standard state, means we are talking about here 25 degrees Celsius, 1 atmospheric pressure. It means from these conditions there is no change in enthalpy. It is there, okay, and it was there. So if these conditions change, there will be some change in enthalpy. But when we start the reaction, we have 1 atmospheric pressure and we have 25 degrees Celsius, that is the room temperature. So at that, in those conditions, we don't have any change in enthalpy. Means change in enthalpy is 0 at that time. So that's why, remember, the standard change in enthalpy for any element is 0. Now the question, the enthalpies of all elements in their standard state, I just talked about it, right? So the enthalpies of all elements in their standard state will always be 0. This is the correct option here.